The last example of a driving force is evolution of a gas. And there are essentially a handful of gases that I need you to recognize. Some you are already familiar with. Things like CO2, NO2, SO2, and H2S, even nitrogen gas. So these are the 5 that I want you to be able to recognize in a chemical reaction. Now, when it comes to actually putting things together that evolve a gas, we can do it in about 2 different ways, I'd say. We can have a reaction where we have a direct formation of one of these gases. Let's say in the case of H2S, we use NaS plus HCl. If we do our replacement, we end up with NaCl plus H2S. Remember, S is the 2- ion here, and so we need 2 hydrogens to balance that out and to make this a complete molecular equation. Let's get our phases in there, and then this is one of those 5 gases. It's what gives rotten eggs its foul odor. And then balancing it, we end up with 2 here and 2 here. So we can write this as a net ionic equation, Na, 2 of them, plus S2- plus 2H plus 2Cl-, producing 2Na plus Cl-, 2 of those as well, and then H2S as a covalent compound as a gas. We would identify our spectators, sodium and chloride will be eliminated, and we are left with S2- with 2H plus, resulting in H2S gas. And this is similar to that neutralization reaction, and we can actually classify this as a neutralization reaction. So you'll see a lot of overlap. So this is a double displacement, it is an acid-base reaction, and it is a neutralization reaction where it forms a weak or non-electrolyte, H2S, which also happens to be a gas. So we have essentially 2 driving forces, and the reason why forming a gas is considered to be a driving force is because it gets removed, much like formation of a solid, gets removed from the reaction phase, right? The reaction is happening in the liquid phase, the gas is bubbling out, and so as you'll learn more about equilibrium and Le Chatelier's principle in the next course, if we remove a product from the reaction, that product is not there and cannot participate in the reverse reaction, for example. So it does drive the reaction towards forming product when you have a product that is removed from the reaction. Let's look at one more example. We just looked at an example where we saw the direct formation of a gas. Another scenario we may see is that we form a compound that is unstable and breaks down into gases. And one of those is carbonic acid. Carbonic acid is unstable and decomposes to water and CO2 gas. And this is an acid that's actually present in your soda. So there is carbon dioxide, and when it's dissolved in water, we actually see some formation of carbonic acid, and so we can shift the equilibrium towards reactants by adding a lot of CO2 and carbonating that beverage. As the CO2 escapes, when we open that can, we start to get the carbonic acid decomposing and forming this CO2 and water. Another compound, H2SO3, would be a case where we get water and sulfur dioxide. Okay, and we could think of a similar example where we are getting the nitrogen dioxide out as a gas. So what does a reaction look like that produces carbonic acid, for example? Well, let's take a strong acid, HCl, and react it with baking soda, sodium bicarbonate. We'll do our displacement reaction, swapping the hydrogen of the acid and the sodium from the base there. This would give me H2CO3, and this initially would be aqueous, and then NaCl. We would note that, H2CO3 is one of those weak acids that is going to decompose into gases. So H2O liquid and CO2 gas are going to be the actual products that we get out of this. So we have our complete molecular equation here. Let's get it to a complete ionic equation. So I have H plus aqueous plus Cl minus aqueous plus Na plus aqueous plus HCO3 minus aqueous. By now you're probably getting to see that this net ionic equation kind of derivation is identical for all of these steps. Water and CO2 are covalent compounds, so they will stay together. And then my soluble strong electrolytes are dissociated. As such, we eliminate any spectators. Those are going to be Cl minus and Na plus. And by taking those out of the equation, we arrive at our net ionic equation. So H plus, HCO3 minus, yield me water and CO2. So we have a gas that's going to bubble out here, and we have a weak electrolyte. Both of them are actually weak non-electrolytes. So again, we see overlap. These types of reactions could be classified as having a driving force of gas evolution or formation of a weak or non-electrolyte. And this is also a type of neutralization reaction because we're dealing with acids and bases. So a lot of overlap here. As you look at these practice problems, you'll get an idea of how to classify these a little bit better. Thanks for watching.